about the unit hydrograph today. So our learning objectives. Are first to define the unit hydrograph. I heard a story about a guy who made it his, I don't know if it was like his COVID goal or his like lifelong, just I want to work on this thing in my life goal to improve his handwriting. And there's like these exercises you can do to kind of really just slow it down, make it a little more legible. After doing all this blackboard work on this pad, I think I might need to do that myself. I don't think it's like night and day, but it's definitely an improvement, according to him.
I started writing block writing like a year and a half ago.
That's what he did. He said he's all caps. Yeah. All caps.
All block writing. Yeah.
I know, right?
Once you get used to it, it's like still it's tough. Like you just write on top. Yeah.
We're gonna try it today. 3.
The back is fast as it used to.
So unit hydrograph are UHs, UH. We're gonna apply UHs to derive a design hydrograph. Look at that, guys. Right before your eyes.
For me, yeah. Like you could barely read
I mean, we all have a lot to work on, Jake. Just kidding. I can't talk, so I'm not going to. All right, so what is a unit hydrograph? The big buildup. I'm going to just write this out, and then we'll kind of look at it together. So if we say, I'll just, yeah. So for a given watershed, the X hour duration unit hydrograph is that watershed, so is its characteristic direct runoff hydrograph. So direct runoff is simply meaning the runoff that directly comes off as a result of the storm. In response to a unit volume so for example 1 inch or 1 centimeter of excess rainfall still going here, applied at a constant rate caps are brutal. For X hours. A unit hydrograph. So we've got a watershed. We've got, we can call it an X hour duration unit hydrograph. We'll just kind of stick with 1 hour. We've got rainfall coming off, and it's a unit rainfall, so 1 inch of rainfall. What is the hydrograph that comes out of that watershed per inch of rainfall, per unit of rainfall, right? And so that unit of rainfall, and I should say excess rainfall, and that's the rainfall that's going to actually run off, not necessarily come out of the sky. All right, so let's get into that a little bit more. So the idea is here that we're going to create a hydrograph. For a watershed. Based on a given, I'm just going to call it like a pulse, right? Or unit of excess rainfall. So just take a look at what this might look like. I've been drawing hydrographs like this where we have this little kind of unit rainfall that comes in. So we'll just call this, 1 inch of rainfall. And so that unit, that pulse comes in, and this is excess rainfall. So we've done a curve number method. We've figured out how much, based on that rainfall, based on the land cover types, how much is actually running off. So this comes from the curve number method. So you do that curve number method, you get that runoff volume or depth from the watershed. And then you're going to have some sort of hydrograph that comes out as a response to that. And the units of this are usually going to be like Q per inch. So CFS per inch of rainfall. And this would just be time. That's your basic unit hydrograph. And there's a number of ways to derive this. We're going to be using some kind of standard SCS methods. Yeah. Yes. Yeah, so constant intensity, right? So here's a rainfall event, and so this is say this is 1 hour, right? 1 hour. And so we have 1 inch over 1 hour, and this is our unit hydrograph. Now, the way this works is it's a linear system, and so we can, we're assuming that unit hydrographs work linearly, meaning we can add them up. So for example, I'll just kind of run through this, what this might look like. Say we're given a hydrograph that looks like this. We have, I'll just draw it normally on the side up. So we have precipitation excess in inches. And say it looks like something like this. We have, this is time in hours. And we have 1 and 2, so inches. So first we have 1 inch, then we have, oh, messed that up here. The faster you move, I think. So if you're going really fast, it knows it once you want to get a lot out of there. Pretty slick. All right. Then we have 2. Then we have 1. Then we have 1. So this is our hydrograph for rainfall. And then this is our unit hydrograph. So if this is our unit hydrograph for each 1 hour constant, right? Constant over 1 hour. So this is our 1 hour duration unit hydrograph, okay, based on a 1 hour storm. So what we can say then is, I'm going to apply this and kind of stack it up or add it up linearly based on these inputs. So I'm just going to just roughly draw this, and we'll do this in Excel. It's a lot easier to do in Excel. So you can imagine in Excel we have time, right, and then we have Q per inch. 0, 1, 2, 3. And then so this hydrograph would just be represented by a bunch of discharge values. Something like that, right? And eventually it's going to come back down to 0. So what I would do is I said, okay, I want to convert this into a normal hydrograph where I have Q and CFS, not CFS per inch, time in hours. I'm going to add all these up, and so I'm going to add up these unit hydrographs. So for my first one, for my first hour, I've got this unit hydrograph, and it goes on for, say, like 10 hours or something like that. So I'm going to kind of squish all these. So it starts, this will be 5, 10. This is going to be real rough, but I'm just going to give you an idea of what this looks like. 1 inch over 1 hour, that's my 1 hour duration. And it goes to about 10 hours, we'll say. So I'm going to just draw that kind of like this. All right, now I've got 2 inches in hour 2. So that's going to start in hour 2. So this one started at hour 0. Start at hour 2, and I've got 2 inches. So I'm going to double that. And it's going to go for about 10 hours. Then I have 1 inch, and then 1 inch. And so these are kind of stacking, and they're starting at different times, right? I've got all these unit hydrographs. Now I'm going to add them up linearly. That's the way unit hydrographs work. And so I just kind of, if I were to do this in Excel, right, I'm starting the next one down here, 1, 5, 8, 9. I start the next one down here, 1, 5, 8. And for the 2 inches, I just multiply this by 2. And then I would add everything up for the Q total, right? 0, 3, 13, etc. So this ends up being my we'll just call it total hydrograph. That's based on adding up all the unit hydrographs that I've scaled from this. So that's a quick overview of how this works. Let's talk about how you would actually derive this from data. So deriving a unit hydrograph. What data would we need? How would we say, okay, I'm going to have, I want to have some data. I've got some rainfall data. I've got some stream flow data. How would I figure out this unit hydrograph? How could I do that? We need a peak discharge. Yeah, we need another peak. It's a good one. So let's think about the pieces here. We need to know the effective rainfall, also known as what runs off, right? The runoff. So I've got a rain gauge, and I've got a hydrograph from that rain gauge, right? So it looks like this. Here's my hydrograph. And then I've got my discharge record. So maybe I have a stream gauge somewhere and I know what the relationship between water depth and discharge is. And so I've got a hydrograph. And it's like base flow, and then we get a hydrograph. So the question is, how do I figure out what is the effective rainfall? This rainfall fell over the watershed, but what actually got converted to runoff? And there's some kind of empirical methods to basically say we can separate out base flow from the storm flow, right? The quick flow. And if I know what the storm flow volume is, and I know what the rainfall volume is, so say storm flow volume in inches, I know that's confusing, but that's kind of often how we do it, rainfall in inches, then I can say, okay, well, of this rainfall, a certain percentage was actually effective. So we had this much rainfall come in, and this is our effective rainfall, also known as runoff. So then I could scale this. I could say, okay, if this is my peak discharge, I could divide it by the total runoff. So I could say here we have Q, we have time, and then we can have Q per inch of rainfall. So say on average, we can kind of like lump this together because it's not going to be a perfect unit duration of rainfall, but say this was a 4-hour event and we had 1.7 inches of effective rainfall. Then I take just these hydrograph values, the Q values, and I would just divide it by that rainfall inches. And so then I would get essentially a unit hydrograph that is Q discharge per inch in time. So I could take data and create a unit hydrograph. Obviously, we don't have these data, and we're often we want to generate unit hydrographs for these small basins that don't actually have, rainfall runoff data. So we'll look at some synthetic methods in a minute.
So would that be the 4-hour?
So in this case, yeah, this would be your if this was a 4-hour storm, your 4-hour duration unit hydrograph. In which case you would have to scale it. So if I have a 4-hour storm, I could add this together in chunks of 4 hours. But usually we're dealing with kind of more basic time bases. So what might be some problems, like the idea that we're going to say, okay, I'm going to say we've got a 4-hour or 1-hour rainfall event. I'm going to create a unit hydrograph out of that. And I want to maybe like have it expand it to a longer storm event, a 12-hour or 6-hour, some kind of storm event. What would be the problems for doing that? We'll just say in one basin or from one basin to the next. But first in one basin, what are some of the limitations or errors we might run into if we tried to do that using this kind of hydrograph in a different setting or storm?
Soil might get saturated and more effective rainfall for future rainfall.
Yeah, so did this storm event happen during a dry spell or a wet spell? So let's just go ahead and clear canvas. So we'll just say problems. how do I want to phrase that? Well, we'll just call it nonlinearity. We have a watershed and you have 1 inch of rainfall over 1 hour, the runoff hydrograph in the summertime versus the springtime versus late fall could be different because you've got different interception, different soil moisture conditions. Maybe the watershed burned, right? A lot of things could change there. Can we transfer this to a different watershed based on what we just did? What do you think, Christian? Because that hydrograph, the shape of it, the timing of everything, the peak relative to the runoff is dependent on that watershed. So if we did this and made this for a watershed, we couldn't necessarily transfer it. What's the intensity of the rain? Is it really heavy? Is it really light? There's a lot of things that could make this. So, and we never have we don't have a perfect, duration rainfall event. It doesn't happen in this perfect chunk of 1 hour, right? Or 2 hours. It's not uniform. So it's definitely a limited tool, but it's a tool that we have and we're going to use. Perfect duration, yeah. Let's go ahead and do it in all caps here. Hydrology is going to be my penmanship lesson, my bi-weekly penmanship lesson. So let's look at a method that we can use. So I talked about kind of the data approach, which is it's usable. I actually did this for my master's thesis. I had 3 watersheds I was looking at. I needed to create some synthetic storms, some synthetic hydrographs. And so I had a watershed, I had a rain gauge in the watershed, and I had a rating curve that told me how high the water was and the relationship between water depth and discharge. So I had those data, and I could create a hydrograph and then divide it right by the runoff volume, separate out that base flow, and create a unit hydrograph. So I actually created a couple unit hydrographs and then scaled those to a bigger rainfall event. So I went to NOAA, Atlas 14, I looked up the 1% AEP. So I got that rainfall depth. And then I scaled that hydrograph so that it looks like a 1 hour, say 6 hour, or sorry, 1% AEP, 6 hour duration rainfall event. So I took that tiny hydrograph and scaled it. Of course, we think about the problems of this. My data was based on a smaller storm, and I'm scaling it up and creating a hydrograph that would probably, the rainfall runoff behaviors are probably going to be really different for a big storm event versus a small storm event. So that's another challenge I'll put there. So scalability, I just call it scalable. Data based on more frequent storm event. Scale to less frequent. And do you remember me talking about the 2013 storm event on the Front Range where we had rain, 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 and then we had a ton more rain. And the water was already, the ground was already saturated. So often a basin, it might even be a forested basin that is already super saturated, then you get another rainfall event on top of it. You could have a huge runoff response similar to an urban landscape that's all paved because the soil's already saturated and we're not infiltrating any water, or the infiltration is really low. So that's another nonlinearity effect, right? That gets back it up here where smaller storms might have less effective runoff, and then larger storms might have more effective runoff as a percentage of the rainfall. All right, so let's look at an actual method for how we might do this. And this is a method not based on data, but based on some simple relationships. And it's called the SCS, Soil Conservation Service Unit Hydrograph. And it's a real simple, kind of the most simple we could do, which is, I'm just really hard to draw straight lines. I'm not gonna lie. Which is a triangle. So the triangle comes up and it goes down. And let's look at some qualities of this. So we'll have Q and CFS first. We've got our Q peak. We've got our couple things here. This would be our time to rise, TR, and then time to fall. In total, we have our base time. And so with this unit hydrograph, we don't actually need to know much information other than basically the time to rise. We need to know the relationship between the rise and fall times and how to estimate the peak discharge. And we can use some basic geometry here. Area of this hydrograph is going to be also the volume, right, of the runoff. If we have cubic feet per second and we integrate that over time, then we'll get a volume, right? Because we're multiplying it by, we're multiplying each of these y values, which is volume per time by time. So we get volume, which is also equal to base times height over 2. All right, so if we'll stick with this volume, right? So volume, also known as area. Edgar, can you tell me what the volume is in terms of Q and T and using these parameters here? We're just using the triangle formula. Yeah. Based on, so relating it to the triangle. 1/2, so if area is 1/2 base times height, what are those analogous parameters from this? So we'll start with volume is equal to 1/2. What's the base? T base. What's the height? Okay, great. Now, we're using these kind of SCS methods. They're pretty old school. They went and looked at a lot of data. They looked at a lot of these rainfall runoff relationships, and they said, we need to make a simple method that people can kind of use everywhere. So they went out and said, what's the relationship between TR and TF? T rise and T fall. And doing a bunch of statistics, they came up with this. They said TR is equal to 1.67 T fall. So it's just a little bit wider. You come up fairly quickly, and then you have this nice recession curve. So this is going to be an empirical relationship from the SES method. Okay. Now let's actually put some numbers to this, a little bit more numbers at least. So we're going to solve for Q peak. Takes longer to fall. Yep. Yes. Yes, thank you. T fall is equal to 1.67 TR. So we have TR, and then we have 1.67 TR. So let's solve for Q peak from this equation up here. Q peak is going to be equal to 2 times the runoff volume all over our T base. Remember, T base is going to be TR plus 1.67 TR, so that's going to be 2.67 TR. And then if we simplify that, we get Q peak is equal to 0.75 times volume all over TR. Okay, great. So now we're going to turn this into a unit hydrograph, because Q peak has units of CFS. This has units of hours, and in this case, volume just has units of volume just has units of. Let's not worry about that right now. I'm gonna have to get back to that one. Convert to unit hydrograph. So if we've got Q peak and CFS, our runoff is actually, so this right here is inches. So this is not dimensionally consistent, but we're going to make it dimensionally consistent in a second here. We got 0.75 times volume, which is in inches, all over our time, TR, which is in hours. And we want to get it so that we can put in some areas and that sort of thing. So we're going to put 640 acres per mile squared. Now we can bring in area. And then we'll bring in a conversion factor, which is 1.008 inches per acre per hour, all over 1 CFS. So now our Q peak equation has some other parameters in it. So it's going to be all those numbers come out to be 484 times area, which has units of miles squared, times volume, which has units of inches, all over TR with units of hours. So if we say that volume is equal to 1 inch, or our unit runoff is equal to 1 inch, then we can just scratch that off. And then we end up with this relatively simple equation, which is our peak discharge is a function of our drainage area and this time to rise. So all we did was this, we said volume is equal to 1 inch. And so this is our basically Q peak, which is just CFS per inch. So peak discharge per inch of runoff volume. Any questions so far? This is a kind of a basic equation. So this gets us our height, right? And it's also a function of our base time. So I'll write that again. So Q peak with CFS per inch units is equal to 484 area, drainage area times TR. So this 484 number, this is basically, you know, this is from all those that unit conversion we did to bring in area. It's called the peak rate factor. And people kind of treat this as a parameter and says, okay, at this peak rate factor, PRF, it could be somewhere between 300 to 600 maybe. This is just a recommendation. There's a reference in your textbook on this. And in HEC HMS, you can actually change this. The default is 484 for this unit hydrograph method. But you could change it. If you have a really low sloped watershed, like on top of the mesa, maybe it's 300, meaning it's a lower number, you'd have a lower peak discharge per unit runoff. So we'll just say like on top of mesa. 600, this is really steep. You have a bigger, a kind of more peak, higher peak factor. This would be something like the Book Cliffs. Where it's really steep, there's not a lot of infiltration happening, that sort of thing. So you could adjust this peak rate factor in HEC HMS to get a bigger peak discharge per unit runoff in inches. So now we can calculate peak, but kind of, we still need to figure out what's this TR. We don't actually know how to estimate this TR. So let's look at that, what that TR actually is a little more closely. So now I'm going to bring in my unit discharge, or my runoff, my precipitation. And this precipitation is going to have a duration D. And we defined this last time for time of concentration. This is my lag time, is the middle of D to the peak of that hydrograph. And TR is when that hydrograph starts to the peak, the time from the start to the peak. So TR really is D over 2, right? We're starting here, this is D over 2, plus the lag time. Does anyone remember what the lag time is related to? That's what we learned last time on Tuesday. Yeah, so that's, yeah, it's the middle of your rainfall event to the peak is the lag time, the definition. But it's also related to time of concentration. Do you remember that? 0.6 times the time of concentration. So our time to rise is d over 2 plus 0.6 times our time of concentration. And we can calculate this based on our watershed properties, right? And that's what we did for that exercise. That's where you guys, Dylan had 18 hours or something like that, and that felt a little high. And Stream Stats does its own calculation, which is a little bit different. So now we can calculate our total. We can do Q peak, right? So we've got Q peak up here, which is our drainage area, and then this time of rise. And then time of rise is a function of the duration of that rainfall event we want to model and the lag time, which is related to the time of concentration. So it's kind of like this Russian doll nested thing. But if we have our time of concentration, and we have our drainage area, ultimately we can calculate our peak discharge and then this unit hydrograph. So let's do an example. And I'll set this up and then I'll have you guys kind of work through it together, okay? Okay, so we have a nice little watershed here. And the area is 10 miles squared. And we did the time of concentration calculation, and we came up with 5.6 hours. So the challenge, or the first step that we're going to do is create a 2-hour duration triangular unit hydrograph. That's going to be step one. And then step two is we're going to apply this to a specified hydrograph, which I'll give you. And I'll set this up. I'll just kind of draw it up for you, and then I'll have you guys actually do the calculations. So here's our unit rainfall events, and we said of D, right? And we said it's a 2-hour duration. We need to calculate our time of rise, which is related to this lag time. And then we also need to calculate our peak discharge. In this case, it's going to be CFS per inch. All right, so let's take a minute or two to calculate peak discharge, time of rise, and then draw this thing out and actually give it some units, right? So tell me what the units are and plot it.
that in terms of just hour or minutes
Everything's in hours. Yep. And I'll just write these out again. Q peak and CFS per inch is equal to 484 area. Units are really important. You know, these equations aren't that complicated, but the units can turn your brain inside out. So it's really important to keep track of everything.
Yeah, 5.6 or
5.6. Yeah, sorry, that's time of concentration. And I'll let you remember how you relate that back to time of concentration. Or you can ask me. 0.6, yep. All right, so what do we get for Q peak? Okay, per inch, right? Per inch of runoff. And then what do we get for TR? Okay. And then the total, the base time is equal to 11.6. So if we want to put some units on here, this is 11.6 hours. And then this is 1010 CFS per inch. So that's our unit hydrograph. All right, the next step is, I'll just keep those numbers here, right? Q peak is equal to
it's a response to a half inch of rain per hour for 2 hours.
yeah. So, and this is our 2-hour duration unit hydrograph.
What did you get 1.1? Oh, it's solid.
And then I'll just do T base. All right, so now we're gonna apply this to a hydrograph. And we'll do a simple hydrograph here. 2-hour duration,
No, today.
OT base. Yeah. Let's do a simple hydrograph. Because I said it's a 2-hour duration, that means the hydrograph needs to have 2-hour chunks of time. And we'll keep it simple. Let's do I'll do 1, 2, so this is excess rainfall in inches, and we would get this from the curve number method. So 1, 2, and 1. Now we might need to do this in Excel, so I'm gonna, well, let's just draw it, because you'd have to do linear interpolation. It's gonna be a little funky, but we'll just draw it. Actually, you know what? I'm gonna give myself a little more space here. So that first unit hydrograph, and this is CFS per inch. This is hours. That first unit hydrograph, it peaked out at 11,000. And it ended, we'll just, well, yeah, whatever, 11.6 hours. So let's say this is 5, 10, 15. So this is what we calculated before. Peaked at 4.36. And because we have the first input in this hydrograph is just 1 inch over 2 hours, or like Jake said, a ½ inch per hour. So just kind of steady, uniform duration rain. Then this is our first input, right? It's just that 1 inch per hour input, okay? CFS per inch. Now the next one is 2 inches. So all I would do is take the Y values here, multiply it by 2, and I'm starting it at hour 2. So if this is 2.5, here's hour 2. And then I'm just going to double it. So we go up here, and this is our double value, so 2220. Remember, our Q peak is 110. Oh, where does it peak? So you look at this and you say, this is the next 2 hour duration. So it starts at 2 hours. And then we just draw the same thing. So it's got the same duration. It's going to start at 2 hours. So it's going to end at 13.6. So kind of right here, 13.6. And it starts at 2 hours. And it's going to go all the way up to the peak is just going to, we're just shifting it, right? So instead of 4.36 hours, it's going to be 6.36 hours. So it's going to be somewhere around here. Just a triangle. And all we're doing is shifting it. It was supposed to be a triangle. Yeah. Yeah, I don't have any other information other than the peak and then the base. All right, and then we have one more. We go back to that unit hydrograph, that same one. It's going to start at hour 4. And it goes up, and then it's going to peak. So we're adding 4 hours. It's going to peak at about 8 right here. Yeah, 1100 says it's 1 inch. And then it'll end 2 hours later, so it's going to end at 15.6. So now what we want to do is take each hour here and add them together to create that total hydrograph that's now scaled. So 0 is going to be 0. We go to hour 1, we just get this, right? Hour 2, it's just this because we're still at 0. Hour 3, we're adding this plus this, so it's going to be a little bit bigger. Let's jump over to hour 5, we get this plus this plus this. So it's going to be, I'm just going to draw it out, guys. Here, where these all meet, we're going to add this plus this. There's 2 hydrographs there, plus this. That's going to be really big. Hour 10, this, plus this, plus this. And then it's going to kind of make its way down, and then it'll end here. So I'm just drawing it out. It's not to scale. It's going to be straight. There's not going to be any bumps in it per se. Well, actually, that's not totally true. There'll be some bumps. But would it be where? It's going to end right here. Maybe do you want to get up and point what you're talking about?
Like we start on the line from the first one, we finish on the line for the.
Oh, so we finish on
11.6 is where this one ends.
That's okay.
If you get up and point on a screen, you can show me what you're talking about.
You want to like come back to that line?
Oh, yes. Would you meet that? Yes, yes, yes. Thank you. So yeah, you would meet this line up and
Okay.
yeah, right there. Thank you for that. Yeah, so we're going to come down, and now that we only have this one, right, it's going to look like that. Thank you, Val. Just like we started on this line, and then we started adding them together. That's why we need to do this in Excel, so you can kind of account for everything. Obviously, drawing it isn't perfect.
painstakingly write out the equation for each interval.
Yeah, that would be painful.
I just started doing it and do it.
Okay. The triangular unit hydrograph, and I show it to you because it's super basic, and it in order to do this in Excel, you'd have to have linear interpolation, right? Because you're trying to add up lines instead of coordinates. So that it's not super straightforward to actually do this, but for illustrative purposes, I can kind of show you how these all add up. What we'll actually use is it's a curvilinear hydrograph, and it's represented as a curve and just a spreadsheet, basically values. So I'll show you what that looks like.
Really quick, can you just go over off of what you have gone and what you're adding together to build that up there?
So if I were to take, maybe I'll draw these as different colors. So I scaled that hydrograph, right? This is ×2,
Yeah.
right? And it started 2 hours later.
Yeah.
And then this one's just ×1. And it started 4 hours later. So all I'm doing is I'm saying for time 1 hour, I take a slice through here and I say, how many hydrographs do I have? Just that one, so it's this value. If I go to time 2, it's still just this one, this is 0. So I'm right here. I'll jump over to time, let's see, just do this. 3 hours, now I'm adding this one plus this one, right?
Oh, I see.
So I jump up a little bit.
So technically, if you got an equation for that line and that line, you're plugging 3 of those equations, and that's what you're adding together.
Once you get over here, you got one. We'll just take this slice, for example. You've got this value, and this value. So all those 3 values add up to make that value. Does that make sense?
Yeah, because that other one, yeah. Okay.
The way you would think about it, say if I had a spreadsheet, I had time, I had hydrograph 1, hydrograph, or just we'll call it Q1, Q2, Q3. And then Q total. So 1, 2, 3, 0, 0, 0, right? And then we'll just say 100 CFS, 0, 0, 200 CFS, 100 CFS, 0. These aren't going to be a perfect correspondence. I guess I should actually try to do that. 0, and then this one, I don't know what the actual value is. No, we're starting to jump up there. 300. Now at 2, this is 0. So now at 3, we actually have a value here. So 200 or 100, we'll say, since no, it's double, so we'll say 200. And then 3 doesn't start till hour 4, so that's going to be 0, 200, 1600. And then this will be 100. We'll peak. We're starting to peak here, so we'll say 2000. Hour 5, we're beyond the peak. We're coming back down. So now we're at, like, say, 900. So now you're adding these up. Right? That's what we're doing here. This slice is just this time, which would be a row.
So when hour 4 on Q1 be greater than hour 5?
Yeah, probably. Yeah, I was just trying to do it illustratively.
Yeah, I see where you're going.
Yeah.
Okay.
So this one is 0 at time 1. Actually, this should be times 0. But yeah, you get the gist.
Right, and that's where the bumps come in you're talking about.
Exactly. So once you start adding, it's going to be a little kind of funky.
Yeah, that one goes down, but the other two going up. Okay. I see it now.
So the SCS one, and I'll show you what that looks like real quick. There's this kind of curvilinear one. And they actually just give you a table of values. And it's a non-dimensional one. So instead of per inch, it's just divided by peak, and this would be time over TR.
Is that when you get into type 1 versus type 2 storms?
Those are going to, those type 1, type 2 storms, I think, refer to the time distribution of the rainfall. So remember, we looked at the distribution curves. That's what that is. And so it says a type 1 is, 50% falls in the first half. Type 2, 75% falls in the first half, something like that. So this is the SCS, and we'll just call it curvilinear. Unit hydrograph. This is what you'll end up using in HEC HMS, and I think for the homework, I'm going to update the homework. So hang on a second, so I have to add, I want to add a unit hydrograph thing to it. I'll give you a table of values. So just the non-dimensional values. So it'll be like 0, 0.1 hour, if this is time, and this would be Q over Q peak. And it's going to go all the way up to 1 and 1, and then it's going to go all the way down again. So this, I think it stops at about 5, and then we go 0. So what you'll do is you can use this, similar to the unit hydrograph, the triangular one that we used, and create kind of a curvilinear hydrograph. And this is just like an average of a bunch of different hydrographs. So we'll use it in the same way. But instead of trying to figure out where the lines add up from the triangular one, you can just add values and fractions. Okay, guys, that's unit hydrograph in a nutshell. you can read if you haven't already in your book. I assigned that, I put that on Canvas. The homework, I'm going to update it, so check it again tonight, and it's going to be based on the last 2 weeks, basically. It'll be due next Friday, yeah.